In the quiet of a world before electricity, nights were guided by flickering candles and the distant glow of stars. Long ago, people gazed up at the skies with wonder, watching lightning split the darkness in brief, brilliant flashes. They felt the gentle tingle of static after walking across a wool carpet or rubbing amber against cloth. These were mysterious passing moments of natural electricity, bright sparks and subtle shocks that came and went, impossible to hold on to. For millennia, light and energy could not be captured or carried. They appeared as if by magic and faded just as quickly, leaving only curiosity in their wake. In those early days of civilization, a steady source of electricity was beyond imagination. Yet, hidden in the sands of time, clues emerged hinting that our ancestors might have sought ways to harness that mysterious force. In a dusty museum display, there rests a humble clay jar discovered near modern-day Baghdad, often called the Baghdad Battery. This ancient pot, dating back nearly 2,000 years, contains a cylinder of copper and an iron rod, with signs it might once have been filled with a mild acid like vinegar or wine. Some quietly wonder if it was an attempt to create a source of power in an age of oil lamps and hand tools. Did it produce a gentle trickle of current to electroplate jewellery or create healing potions? We may never know for sure. The jar sits silently behind glass, an enigma from history's dawn, inviting us to imagine a soft glow of innovation in those distant times. Perhaps long ago, a curious artisan poured a bit of sour wine into such a jar, dropped in the copper cylinder and covered it. If wires and metals were attached just right, a feeble current might have flowed, too faint to see, but enough to tingle at a touch. Maybe it was used to apply a thin coating of gold onto a small trinket, or to startle an onlooker with a gentle shock, demonstrating a hidden power. Or perhaps this ancient pot was not a battery at all, but simply a storage vessel, and its resemblance to modern cells is a coincidence. The truth remains a quiet mystery. Still, the possibility that even in antiquity someone toyed with capturing electricity adds a dreamy prologue to our tale. For countless generations after, the secret of stored electricity remained elusive. People could only observe its fleeting dance. Ancient Greeks noticed that rubbing amber would cause feathers or dry leaves to cling, a gentle and almost magical attraction. The word electric itself comes from electron, the Greek word for amber, but these crackling sparks were momentary. There was no apparatus to carry or preserve that energy. People also learned of electricity in living creatures. The ancient Romans and Greeks, for instance, knew of certain fish, like the electric ray in the sea or the shock of a catfish in the Nile, that could jolt a person who touched them. Some even used these fish as a crude therapy for headaches or gout, letting the animal's natural electricity numb the pain. Yet these occurrences were as brief and uncontrollable as a lightning flash or a static spark. After the spark, darkness and stillness returned. Humanity had long found ways to store other forms of energy, keeping embers glowing under ash to preserve fire through the night, drying food and storing grain to carry sustenance through winter. But capturing electrical energy posed a new challenge. Electricity was like a mischievous sprite, visible only in the instant of its spark, then gone. To grasp and hold this force would require patience, imagination, and many gentle experiments over centuries. The dream was to tame lightning into a bottle, to have at hand a controllable spark, a steady current that could be called upon as reliably as the stored warmth of a hearth. In time, that dream would slowly come to life. Centuries passed in relative quiet on the electrical front. The world lit its nights with fire and rested under skies undisturbed by the hum of any machine. It was not until the early 1600s that scholars began to systematically explore nature's subtle forces. In England, a physician named William Gilbert studied magnetism and static electricity. By carefully observing how amber, when polished and warmed by hand, would attract small bits of paper, Gilbert gave this subtle force a name, the electric force. His work, while quiet and meticulous, laid a foundation for thinking about electricity as a real phenomenon in the natural world. Still, even Gilbert's electricity was a brief attraction, a gentle curiosity. There was no hint yet of a continuous current or a device to store this strange new force. From the stillness of the scientific libraries of the 17th century, we move into the lively curiosity of the 18th century. an era of experiments performed in drawing rooms and makeshift laboratories. In the mid-1700s, a new invention appeared that could hold an electrical charge, if only for a moment. This was the Leyden jar, a simple glass jar lined with metal on the inside and outside, with a metal rod piercing its cork. When the rod was touched by a source of static electricity, like a rubbed glass tube or a spinning globe of sulfur, the jar would quietly accumulate charge. In a sudden flash, it could release a spark, a tiny bolt of lightning in the experimenter's hand. It was as if one could bottle the lightning, capturing a piece of the storm in a humble jar. Scientists and enthusiasts across Europe took to charging Leyden jars and playfully shocking themselves or their friends, feeling the jolt as a mix of surprise and curiosity. The Leyden jar did not provide a steady flow of power, only a single burst. But for the first time, electricity could be stored, albeit briefly, and carried from one place to another. Around this time, an American inventor and thinker named Benjamin Franklin was also delving into the mysteries of electricity. Franklin famously flew a kite under stormy skies to draw down electricity from the clouds. On a cloudy summer afternoon, he launched a simple silken paper kite into the air, its wet hemp string trailing down to a key tied near his hand. He kept hold of a dry silk ribbon attached to the string to insulate himself for safety. Lightning flashed silently in the distance as the storm approached. Franklin noticed the loose fibers of the string begin to stand on end, a sign that the string was becoming charged. Carefully he moved his knuckle near the metal key and saw a small spark jump to it. That gentle spark was proof. Electricity from the thunderclouds had travelled down the line. It was not a dangerous lightning bolt striking him, but a soft crackle of static that he coaxed from the sky. With that experiment, Franklin demonstrated that lightning was indeed the same mysterious electricity that one could produce with a Leyden jar. In safer experiments in his Philadelphia workshop, Franklin used multiple Leyden jars linked together to increase the amount of charge that could be held. He likened this setup to a battery of cannons firing together, and from that inspiration, he borrowed the term battery to describe an array of charged jars acting in unison. Franklin's electric battery of Leyden jars was not a battery in the modern chemical sense, but the name stuck. It captured the idea of many small power sources working together to create a stronger effect. And so, softly, the word battery entered the language of science, a term that would eventually come to mean so much more in the centuries ahead. Even with these advances, all electrical phenomena so far were still fleeting and largely impractical. They were sparks from friction or charges stored briefly on glass. The world still waited for a gentler, continuous flow of electricity, a current that could be harnessed to do work steadily, like a calm stream instead of a sudden thunderclap. The stage was set, though the main actors had yet to arrive. In the late 18th century, nature provided a subtle hint towards the next great step, and it came from an unexpected source: the twitch of a frog's legs. In the 1780s, across the ocean in the quiet town of Bologna, Italy, a scientist named Luigi Galvani conducted experiments in the lamplight of his laboratory. Galvani was studying anatomy and the effects of electricity on muscle, and one evening he noticed something peculiar. On his table lay the legs of a frog, prepared for dissection. When his assistant touched a nerve in the frog's leg with a metal scalpel that had picked up a static charge, the leg gave a sudden small kick. In the stillness of that Italian evening, it seemed as if the lifeless frog had momentarily come back to life. Galvani was fascinated. He hung frog legs from iron railings during thunderstorms and saw them twitch as if plucked by invisible strings. He came to believe that the frogs were revealing a kind of animal electricity, a vital fluid or force inherent in living tissue. It was a gentle, natural electricity, he thought, flowing through muscles and nerves. Galvani's findings spread curiosity through the scientific community. One who took great interest was Galvani's friend and fellow scientist, a physicist named Alessandro Volta. Volta lived in the north of Italy near Lake Como with a calm and methodical mind. He wasn't entirely convinced by the idea of a special life force in the frog's nerves. Volta suspected that the key to the frog leg's kick was not some unique animal fluid, but rather the presence of two different metals touching the moist muscle tissue. To Volta, it hinted that the metals themselves, with the frog's body acting as a conductor, were creating an electric circuit, In essence, the frog was serving as a bridge between two different metals, allowing electricity to flow. Night after night in the quiet of his study, Alessandro Volta experimented to test this idea. He layered different metals and materials, seeking a combination that would produce a steady electrical effect. He tried many pairs of metals, copper with tin, silver with zinc and others, placing thin pieces of cloth soaked in salt water between them. Some combinations produced a stronger effect than others, which he carefully noted. By 1799, Volta found success. He discovered that by stacking discs of two unlike metals, such as zinc and copper, separated by cloth or paper soaked in saltwater brine, he could create a gentle, continuous electric current. It was a small current, but it flowed steadily as long as the stack remained moist and intact. This invention became known as the Voltic pile, the first true battery. Imagine Alessandro Volta in his candlelit laboratory, carefully piling the metal discs one atop the other. Copper, then zinc, then copper again, building a column of repeating layers. Between each metal pair, a piece of cloth dampened with salty water serves as a separator. As he connects a wire to the top and bottom of this pile, a soft current begins to flow through the wire, unseen but real enough to be felt as a tingle or observed by its effects. There is no dramatic spark or shock. Instead, it is as gentle as water seeping through sand, yet continuous and reliable. Volta has given the world a way to store and release electricity through chemistry quietly and persistently. Word of Volta's creation spreads through Europe like a gentle murmur. He writes letters describing his artificial electric organ and the continuous stream of electricity it provides. In 1800, he formally publishes his discovery, and soon scientists everywhere are recreating Volta's pile. They marvel at how it can keep delivering power for hours, a wonder at a time when no other device can do so. In Paris, the great Napoleon Bonaparte himself takes interest and invites Volta to demonstrate this invention. Volta travels to France and, in 1801, before an audience at the National Institute, he shows the Voltic pile in action. One can picture the quiet in the room as the men of science lean in, eyes widened slightly in the lamplight, while Volta connects wires to his stack of metal and salty cloth. Needles on instruments flicker, small shocks are felt, and chemical reactions are induced, all through the tame, steady flow from this column of metal discs. It is a subdued kind of magic, not the crash of thunder, but the steady glow of a new light. The Voltic pile is simple, yet it unlocks so many possibilities. Soon, others are experimenting with the larger piles and different metals. Scientists discover that by linking many of Volta's cells in series, they can produce higher voltages, and by making the cells bigger, they can supply more current. In laboratories, the gentle hiss of bubbles can be heard as experimenters use these batteries to decompose water into hydrogen and oxygen. Metals are isolated from their compounds. The English chemist Humphrey Davy builds a great battery with hundreds of metal plates and uses its current to coax new elements like sodium and potassium out of their bonds, producing tiny bright globules of metal that dance on water. Each new experiment is like a small steady step forward into the electrical age, taken without hurry. Volta's first batteries, though groundbreaking, have their imperfections. After some time, the current from a Voltic pile weakens. In the stillness of the lab, a careful observer might notice why. Small bubbles of gas form on the copper plates, hydrogen gas, a byproduct of the current, gradually insulating the plate and impeding the flow. The zinc also slowly dissolves, and impurities in the metal cause little local currents that eat away at it without contributing to the main circuit. Early batteries might only last an hour or two before they need to be refreshed with new chemicals or reassembled. But even these challenges quietly guide inventors toward improvements. In 1835, an English inventor named William Sturgeon finds that coating the zinc with mercury, a process called amalgamation, helps prevent those tiny side reactions. This simple treatment allows the battery to deliver a steadier output for a longer time, alleviating one of the pile's problems. Many minds tinker and refine, seeking a battery that will last longer and provide a more stable current. Despite its flaws, Volta's battery provides a far steadier current than any Leyden jar could, and it makes possible many new experiments and discoveries. One such experiment takes place in 1800 when two scientists, William Nicholson and Anthony Carlisle, connect wires from a voltaic pile into a glass of water. They observe streams of tiny bubbles forming at each wire, one side releasing hydrogen gas and the other oxygen. The water is slowly being split into its components by the steady current. It is a quiet and marvellously clear demonstration of the power now at their fingertips. Using the new battery, they have decomposed water itself, revealing its secrets bubble by bubble. By the middle of the 19th century, the landscape of batteries has broadened. Scientists have learned to make electricity flow longer and more reliably. But one limitation lingers over all these primary batteries. Once the chemicals inside are used up, the battery stops producing current and becomes a spent, lifeless cell. The only way to get power again is to replace the chemicals or build a fresh cell. It is as if each battery is a single-use container destined to go dry. In an age where reusability is valued, this impermanence quietly nags at inventors. To appreciate this challenge, it helps to think about what was happening inside a battery. As the cell produced power, its chemicals were being consumed or transformed, like wood slowly burning to release energy, except here the process was electrochemical and often invisible. Once the active ingredients were used up, the battery had nothing more to give. The idea of a rechargeable battery meant finding a way to reverse those chemical changes by feeding energy back in. It would be akin to turning ash and smoke back into wood, a concept that seemed almost against nature. Yet, some inventors wondered if with the right materials and conditions, such a reversal could be achieved, allowing a battery to be used over and over. And so, the next great chapter in battery history is about giving these cells a sort of rebirth, finding a way to use them over and over again. The solution comes from a soft-spoken French physicist named Gaston Planté in 1859. Planté is intrigued by the idea of a secondary battery, one that could be discharged and then recharged, like winding up a clockwork toy after it has run down. He begins experimenting with sheets of lead, a heavy metal familiar to chemists of the day. In his laboratory, Planté rolls up two long, thin strips of lead, separating them with cloth into a tight spiral, and immerses this assembly in a jar of dilute sulfuric acid. The device he creates looks a bit like two coiled ribbons nestled together. When he first charges this arrangement, by connecting it to a source of current, for example, another battery or a primitive generator, he finds that one of the lead sheets slowly becomes coated with a brown layer of lead dioxide, while the other remains as spongy metallic lead. He has, in essence, created two different lead-based electrodes through that initial charging process. When Planté then disconnects his charging source and connects the two lead sheets together via a wire, a current flows. The lead and lead dioxide react with the sulfuric acid to generate electricity, gradually turning both electrodes into lead sulfate in the process. Planté has invented the lead-acid battery, the first rechargeable battery. After the cell discharges and the current stops, Planté discovers that by applying current again, essentially pushing electricity back in, the lead sulfate can be driven back to lead metal and lead dioxide on the respective plates, restoring the cell's ability to produce electricity once more. It is revolutionary, a battery that does not die after one use, but can be rejuvenated again and again by feeding it energy. Imagine the scene in Planté's workshop in the late 1850s, a quiet space with glass jars and metal coils, the air carrying a faint smell of acid. Planté watches a small telegraph instrument author light glow from his lead-acid cell, then dim as the battery's energy is drained. Instead of disposing of the spent cell, he reconnects it to his charging device and gently bubbles current through it. After some time, as if refreshed, the battery can produce power again, lighting the lamp once more. It is a subtle kind of renewal, like watering a wilted plant and seeing it slowly lift its leaves. The world now has not just a battery, but a rechargeable battery, a concept that will become the backbone of countless technologies in years to come. Planté's lead-acid battery is heavy and at first quite low in capacity. Early on, it is more a scientific curiosity than a practical power source. But over the next couple of decades, improvements trickle in. In 1881, another French scientist named Camille Faure finds a way to make the lead-acid battery more practical by changing its construction. Instead of using plain lead sheets that take a long time to form into active material, 4 coats lead oxide paste onto lead grids. This dramatically increases the surface area for the chemical reactions and the battery's capacity to hold charge. The improved cells can be made more compact and store much more energy. With Faux's innovation, the lead-acid battery quietly becomes a staple source of portable power for heavier tasks. By the late 19th century, one could find lead-acid batteries being used in places where a moderate amount of electricity was needed reliably. They were installed in telegraph offices and laboratories as backup power sources. Early telephone exchanges sometimes kept lead-acid cells charged to ensure the lines stayed active. And as the 20th century approached, lead-acid batteries found their way into transportation. In the 1890s, quiet electric carriages rolled through city streets, powered by banks of lead-acid cells. These early electric cars moved without the noise or fumes of combustion. One could hear only the soft whir of the motor and the rumble of wheels on cobblestone. For a time, around 1900, electric cars even outnumbered gasoline cars in some cities, prized for their clean and effortless operation, no hand cranking required to start. Though these electric vehicles were eventually eclipsed by gasoline-powered cars with their longer range and quick refueling, one could sense even then that storing electricity for motion was an idea with a long future ahead. In 1912, another important role for the lead-acid battery emerges in the world of automobiles. That year, Cadillac introduces an electric starter motor in one of its cars, eliminating the arduous task of hand-cranking the engine. This starter is powered by a lead-acid battery, and it proves so convenient that it soon becomes standard across the industry. From then on, even gasoline-powered cars carry a battery on board, a quiet, unseen helper that provides the spark to start the engine and power the lights and ignition. The lead-acid battery thus becomes an essential component of virtually every car, quietly doing its duty each time someone turns the key or presses the start button to set off on a drive. Before we talk about the next new battery chemistry, another piece in the evolution of batteries unfolded in the mid-1800s. The success of Volta's and Daniel's cells spurred others to refine and tailor batteries for different needs. In 1837, a physician named Goldingberg experimented with a variant of the Daniel cell using a plaster of Paris barrier to hold the fluids apart, an idea useful in the budding field of electroplating. In 1839, a Welsh judge and inventor named William Grove took a different approach. He combined zinc in a dilute sulfuric acid solution and platinum in a nitric acid solution, separated by a porous pot. Grove's cell produced a higher voltage, nearly twice that of a Daniel cell, and was eagerly adopted in laboratories for its powerful output. Its design had a clever feature. The chemical reactions in Grove's cell consumed the hydrogen gas that would otherwise bubble and weaken the current, by letting that hydrogen combine with nitric acid. This meant Grove's battery could deliver strong current until its fluids were exhausted, without the same quick polarization that plagued Volta's original pile. Another inventor, the German chemist Robert Bunsen, found a way to improve on Grove's idea in 1842 by replacing the expensive platinum electrode with sticks of carbon in the nitric acid half of the cell. Bunsen's cells gave off a pungent whiff of oxides from the nitric acid, so they were not something you'd want in your parlour, but they provided reliable, strong currents for early electric arc lamps and industrial experiments. Each of these developments was like a gentle variation in a long melody, improving here, adjusting there, always seeking a more steady and convenient source of electrical power. In the same era, William Grove also demonstrated an unusual device that did not consume metal at all. He set up a pair of platinum electrodes, one in a jar of hydrogen gas and the other in a jar of oxygen gas, both linked by a dilute acid solution. When connected in a circuit, these gases combined to form water and, in the process, generated a small electric current. This invention, later called the fuel cell, was essentially the reverse of electrolysis. Instead of using electricity to split water into hydrogen and oxygen, it used hydrogen and oxygen to produce electricity and water. Grove's fuel cell was a gentle curiosity of the laboratory, its only exhaust a few drops of water. Though it wouldn't find practical use for over a century, it quietly proved another principle. Electricity could be generated not only by consuming solid metals, but also by combining gases. It was a profoundly new idea, demonstrated without fanfare, showing that chemical energy could be converted to electrical energy in more than one way. This early fuel cell was ahead of its time, a laboratory marvel that hinted at technologies far in the future, where feeding fuel into a cell could produce a steady electric current. By the middle of the 19th century, the panorama of battery technology had grown richer. Scientists and engineers now had an assortment of cells. Some gave high voltages, some lasted longer, some were safer or cheaper. But all of them, up to the invention of Plante's lead-acid cell, were primary batteries, use-once arrangements. The idea that a battery could be used, recharged and used again was a turning point in concept. The lead-acid battery gradually made its way from laboratory novelty to practical device. It was heavy and bulky, but its ability to be recharged lent it to uses that justified the weight. We've seen it powering vehicles and providing backup power. It's worth noting that the Daniell cell, even as newer batteries emerged, remained in use for quite some time because of its reliability. Indeed, the Daniell cell's stable output, about 1.1 volts, was so dependable that it became an early standard for defining the unit of electromotive force. For a while, the volt itself was calibrated against the steady voltage of a well-made Daniell cell. Around the same mid-1800s period, another important innovation occurred that would shape the batteries to come. In 1866, a French engineer named Georges Leclanché devised a battery that was simpler and well-suited to intermittent use. The Leclanché cell consisted of a zinc anode, a rod, and a cathode made of crushed manganese dioxide mixed with a bit of carbon, all immersed in a solution of ammonium chloride, a salty brine. The manganese dioxide acted as a depolarizer, quietly absorbing the hydrogen gas that tended to form and would otherwise diminish the current. The Leclanché cell produced about 1.4 volts and could deliver small spurts of current, perfect for the new inventions of the time like doorbells and telegraph sounders, which needed brief pulses of electricity. The Leclanché cell quickly gained popularity in telegraphy, railway signalling, and to power the ringing of electric bells. It had the advantage of being relatively inexpensive and easy to maintain. If one were to visit a typical late 19th century home, one might find a Leclanché cell or two in a wooden box connected to the front doorbell. When a visitor pressed the button at the door, the circuit closed and the cell sent a jolt of current to the bell, emitting a cheerful ring. Early telephone systems also adopted Leclanché cells. Each telephone had its own local battery, often a pair of Leclanché wet cells, to provide the power for transmitting voices. As long as the conversation was brief or intermittent, these cells performed adequately, and if given a little rest, they would recover somewhat between uses. In lengthy conversations, however, a Leclanché cell would gradually run down, the voltage sagging as the internal resistance grew. People learned to pause naturally during calls, giving their little batteries a moment to recuperate so the words would remain audible. If the voices grew faint, it was often because the batteries were running low. If that happened, the remedy was to replace or rejuvenate the spent cells, a small chore of maintaining the new conveniences. Many households kept spare battery jars or packs ready, just as they kept oil for lamps to ensure their doorbells and telephones stayed operational. Tending to one's batteries became a part of everyday life, not unlike winding a clock or trimming a lamp wick in earlier times. Georges Leclanché's original cell was a wet cell, meaning it had liquid electrolyte that could spill, so it worked best sitting upright in a box. But the principles of his design laid the groundwork for something even more convenient. The true dry cell, where the electrolyte would be immobilized and the battery sealed. Over the next 20 years or so, inventors tried to transform the Leclanché chemistry into a fully portable form. Various experiments were made, mixing the ammonium chloride solution with materials like starch, sawdust, or gelatin to create a paste. The challenge was to keep the electrolyte moist enough to conduct ions but bound so it wouldn't leak. In 1886, a German scientist named Karl Gassner succeeded in this quest. He devised a version of the zinc-carbon battery, which is essentially what the Leclanché cell is, in which the ammonium chloride electrolyte was mixed with plaster of Paris and a little zinc chloride to form a gel-like paste. He packed the manganese dioxide and carbon mixture around a carbon rod, the positive electrode, and used a zinc cup as both the container and the negative electrode. Crucially, because everything was sealed and the electrolyte was not free to slosh around, This dry cell could operate in any orientation without spilling. It provided about 1.5 volts and had a decent shelf life when not in use. Unlike previous wet cells, Gassner's dry cell required no maintenance. One could simply use it until it was exhausted, then replace it. No need to top off fluids or clean electrodes regularly. By the 1890s, dry cells began to be mass-produced. In 1896, the first widely marketed dry cell, the Columbia dry cell, appeared in the United States. It was soon followed by others, and by the turn of the century, ordinary people could buy these batteries in hardware stores. It was the first convenient battery for the masses, making truly portable electrical devices practical. One direct outcome of this was the invention of the flashlight, or electric torch. In 1899, a few inventors combined a small incandescent light bulb with a simple switch and a pair of dry cells in a handheld device. Early flashlights were quite dim, and the batteries did not last long. In fact, they were named flashlights because one would use them in brief flashes to conserve power. But they were revolutionary. Imagine being able to walk through a dark house, or a forest path carrying a safe, battery-powered light in your hand, rather than a candle or kerosene lamp. The dry cell made this possible, providing a sense of safety and convenience previously unknown. Over time, as dry cells improved, the flashlight evolved into a reliable, steady light source that many took on evening walks or kept by the bedside for emergencies. By the early 20th century, batteries were taking standardized shapes and sizes. Manufacturers introduced cells in standard dimensions with letter designations: large D cells for lanterns and flashlights, C cells for mid-sized lamps and toys, and smaller AA and AAA cells for tiny flashlights, and later for radios and gadgets. Even the now familiar 9-volt battery, a little rectangular pack of cells, would appear by the mid-20th century. This meant that as new battery-powered devices came to market, consumers could easily find the right battery off the shelf. The battery had become a commodity, a quiet companion to everyday life, ready to serve when called upon. Across continents and under oceans, telegraph wires were being strung up, carrying pulses of electricity that encoded messages in Morse code. Those pulses needed a reliable heart to drive them, a source of electrons to send racing down the line. The Daniell cell, with its steady output, became that heart. In telegraph offices from London to New York, one could find rows of glass jars on shelves, each holding a blue vitriol of copper sulfate solution with a piece of copper and a porous cup containing zinc and acid. These jars sat quietly bubbling, providing the lifeblood of the communication network. A faint smell of acid and metal often hung around these battery shelves, a tang of vinegar and mineral that telegraph operators came to recognize as the scent of electricity at work. Some telegraph offices used a variant of the Daniell design called a gravity cell, which had no separating cup at all. Instead, the heavier copper sulfate solution stayed at the bottom of the glass jar, and the lighter zinc sulfate solution formed a clear layer on top. As long as the jar was not disturbed, the two layers remained apart by their own weight, and the cell worked efficiently. Operators could glance at the jar and see its health in the colours. Vibrant blue below and a nearly colourless liquid above indicated the cell was in balance. These gravity cells, too, quietly powered the lines for months on end. An operator would tap out a message, and somewhere on a shelf, a chemical reaction in a jar would dutifully send a pulse down the wire. It was as if the distant flicker of Volta's first pile had now grown into a steady, planet-spanning heartbeat of electricity. The use of batteries in telegraphy had truly brought electricity out of the lab and into the wider world. Messages that once took weeks by ship could travel in minutes via copper wire, all powered by those silent chemical reactions. Soon, in homes and offices, other innovations followed. The doorbell, a simple circuit where pressing a button let a battery send current through a bell coil, and the telephone, which, in its early years, relied on local batteries for each handset to transmit voices. By the late 19th century, one could say that society was entering an electrical age. Though the hum of generators and the reach of power lines had not yet spread everywhere, batteries were bridging that gap, quietly enabling communication and convenience wherever a wire could not yet reach from a distant dynamo. Through the first half of the 20th century, the pattern in battery development was one of steady, incremental progress. Batteries improved quietly in laboratories and factories, while in the outside world they became more and more a part of ordinary life. By the 1920s and 1930s, many households without access to urban power grids still enjoyed the benefits of radio, thanks to batteries. A family in a rural farmhouse might have a set of batteries powering their radio receiver, often a large 6-volt lead-acid battery, recharged from time to time by a wind generator or by bringing it to a charging station in town, and some dry cells for the higher voltage needs of the radio's vacuum tubes. Listening to news or music on the radio in the evening, they would be scarcely aware that a quiet electrochemical drama was playing out in the battery box nearby, converting stored chemical energy into the gentle electric currents that made the speaker hum. World events also pushed battery technology forward. During the 1940s, the demands of World War II required reliable portable power for field radios, flashlights, mine detectors, and a host of other equipment. Engineers responded with new designs and improvements. One notable innovation of that era was the mercury battery, also known as the mercury cell, invented by Samuel Rubin in 1942. This small, very stable battery used zinc as the anode and mercuric oxide as the cathode, with a strongly alkaline electrolyte. Mercury batteries had an excellent shelf life and provided a steady voltage output. They were made in compact forms, button cells, ideal for devices like hearing aids, or for the small electronic circuits in proximity fuses. After the war, mercury batteries became common in things like hearing aids, cameras, and early electronic watches. They quietly powered these devices with a long-lasting and dependable output, though in later decades they would be phased out due to environmental concerns over mercury. As the 1950s arrived, the consumer market for portable electronics was on the cusp of a boom. The invention of the transistor meant that radios could become small and pocketable, and many other gadgets were poised to enter daily life, all needing better batteries. The common zinc-carbon dry cells were widely used, but they had limited capacity, especially under the heavier loads of motorized toys or the new transistor radios. It was time for another leap in primary battery technology. This leap came from revisiting an older idea, the alkaline battery. A Canadian engineer named Louis Urry, working in a battery company's research lab, took on the challenge of extending the life of ordinary batteries. Building on earlier work, Thomas Edison himself had investigated alkaline solutions in batteries decades before. Urry decided to try a design using an alkaline electrolyte, potassium hydroxide, instead of the acidic ammonium chloride used in zinc-carbon cells. By the mid-1950s, he had prototypes that significantly outlasted traditional cells. The chemistry was still zinc and manganese dioxide, a tried-and-true combination, but the alkaline environment reduced corrosion and allowed more of the zinc to be utilized. Urry's battery also used powdered zinc, giving a much larger surface area for reactions. The result was a cell that could deliver substantially more total energy and handle higher current draws without dropping in voltage so quickly. By 1959, the first alkaline manganese batteries were introduced to the market. They lasted several times longer than the old zinc-carbon cells in many applications. For consumers, this was a quiet revolution. A portable radio could play much longer on one set of alkalines. A child's toy train could run and run without the early fade everyone had come to expect from the old batteries. Over the 1960s, alkaline batteries became increasingly popular and affordable. Brands like Eveready, later Energizer, and Duracell became household names by packaging and marketing these long-lasting batteries for flashlights, cameras, and toys. By the 1970s, the alkaline battery had largely taken over as the primary disposable battery of choice, and zinc-carbon cells were relegated to budget uses. The alkaline battery had given portable electronics a stronger, steadier heartbeat, all while remaining as straightforward to use as dropping a cell into a compartment and flicking a switch. While primary, single-use batteries were reaching new heights of performance, the world also saw parallel progress in secondary, rechargeable batteries during the mid-20th century. Here, the seeds planted by Plante's lead-acid cell and Jungner's work in the 1890s began to fully sprout. Rechargeable batteries would become crucial for many emerging technologies, from aerospace to home electronics. In 1899, the same year that saw the dry cell rise to prominence, a Swedish inventor named Waldemar Jungner introduced another new battery chemistry, the nickel-cadmium battery, often abbreviated NICD or NiCad. Instead of lead and acid, Youngner's battery used a positive electrode made of nickel oxyhydroxide and a negative electrode made of cadmium metal with a potassium hydroxide alkaline electrolyte. The nickel-cadmium cell produced about 1.2 volts, a bit lower than a fresh zinc carbon or alkaline cell, but it had a remarkable property: it was rechargeable. Like Plante's battery, once the nickel-cadmium cell discharged, it could be charged again by applying an external current, reversing its internal chemical reactions. The nickel-cadmium battery was also robust in delivering high currents, and could be drained and recharged many times. However, nickel-cadmium batteries were more expensive to produce than lead-acid. Both nickel and cadmium were costly materials, and early on they had some quirks, like a tendency to develop a memory effect if not discharged fully before recharging. So for many decades, nickel-cadmium batteries were used only in situations where their particular strengths, lighter weight than lead-acid and able to supply relatively high currents for their size, warranted the extra cost. One early niche was in the realm of portable lighting for mining or photography. Another was in laboratory settings. By the mid-20th century, sealed nickel-cadmium batteries, often in the form of cylindrical cells that looked much like alkaline batteries, became available and started appearing in things like handheld two-way radios and some early cordless appliances. Interestingly, as early as the late 1950s, nickel-cadmium cells found use beyond Earth. Some of the first satellites launched into orbit used nickel-cadmium rechargeable batteries to store energy from solar panels. These batteries would charge as the satellite was in sunlight, then discharge to power the spacecraft during the dark portion of its orbit. NECD chemistry proved durable enough to handle the constant cycling in the harsh environment of space. For example, the Vanguard the Wee satellite launched in 1958 carried nickel-cadmium batteries that operated for years. This quiet service in space was a testament to how far battery reliability had come. A concept first proven with a frog's leg and Volta's discs was now enabling artificial moons to communicate from the heavens. By the 1960s and 70s, rechargeable batteries began to quietly revolutionize small appliances and tools on Earth as well. For the first time, devices like electric shavers and portable drills could be used without being plugged into the wall, powered instead by internal nickel-cadmium battery packs. These early cordless gadgets often needed recharging after only a short period of use and were a bit heavy due to the batteries, but they offered a new kind of freedom. No longer was every appliance tethered by a cord. A hint of the mobile convenience that would define later decades was emerging, powered by those rechargeable cells. For instance, a handyman in 1975 might carry one of the first cordless drills, using it on a rooftop far from the nearest outlet, then dutifully placing its nickel-cadmium battery on a charger at lunch so it would have enough energy to finish the day's work. It was a small taste of a cordless future. Another pioneering spirit in the realm of batteries was the famous American inventor Thomas Edison. In the late 1890s, Edison turned a great deal of his inventive energy toward developing a better battery, specifically with electric vehicles in mind. He reasoned that if he could create a battery that was lighter and more robust than lead-acid, it could make electric cars, which at the time were, still competing with steam and gasoline vehicles, the dominant technology. Edison and his team spent years testing thousands of combinations of materials. By 1901, he introduced an alkaline storage battery with an iron anode and a nickel oxide cathode, using a potassium hydroxide electrolyte, the nickel-ion battery. Edison's nickel-ion cells were durable and could last through many charge-discharge cycles. They were also less prone to certain types of degradation that affected lead-acid batteries. However, they had some downsides. They were relatively heavy for the amount of energy they stored, and they vented hydrogen gas when charged, meaning they needed maintenance and could not be sealed completely. Edison's dream was to power the transportation of the future, but by the time he had a practical version of his battery, gasoline cars had surged ahead, aided by their longer range and the convenience of quick refueling. In 1908, Ford's Model T began to roll off assembly lines, and cheap gasoline fuel became widely available, a combination that overshadowed electric cars for decades to come. Edison's battery, though, did not go to waste. It found great success in other applications. His nickel-ion batteries were used in railroad signaling systems, providing reliable backup power to switch signals and lights. They were also adopted in mining, where battery-powered cap lamps on miners' helmets were far safer than open flames. Edison's cells, rugged and long-lived, were well suited to the bumps and jolts of mine work. It wasn't uncommon for an Edison battery, with proper care, to last 20 years or more. Some of these batteries, manufactured in the early 1900s, astonishingly still hold a charge in modern times, quietly testifying to their resilience. Edison may not have won the automotive battery race of his day, but his contributions added another thread to the tapestry of battery technology, one that emphasized longevity and durability. As the 20th century progressed, the presence of batteries in daily life became ubiquitous. They powered flashlights for nighttime walks and emergencies, they sat in the bottoms of radios and later transistorized portable music players, and they found their way into cameras, toys, and countless gadgets. Disposable batteries, like alkalines, provided convenience for moderate use, while rechargeables, like NISAIDs, were employed for more intensive or specialized uses. The 1980s brought another rechargeable option for consumers, the nickel metal hydride battery, NiMH. Nickel metal hydride batteries were an outgrowth of work on nickel hydrogen batteries, which were used in aerospace. Instead of using a cadmium negative electrode like NiCd, the nickel metal hydride cell uses an alloy that can absorb hydrogen. When charged, the alloy stores hydrogen atoms. When discharging, those hydrogen atoms are released to react with the hydroxide in the electrolyte. The positive electrode is much like NiCd's, nickel oxyhydroxide. The elimination of cadmium, a toxic metal, and an increase in energy density were key advantages of NiMH. By 1989, NiMH rechargeable batteries became available to consumers in common sizes like AA. They offered more energy storage than nickel cadmiums of the same size, and didn't suffer as severely from memory effect. Soon, many people were using NiMH cells in their cameras, portable music players, and other devices, enjoying the ability to use them over and over again. In fact, NiMH technology became the linchpin of the early hybrid vehicles around the year 2000. Automakers adopted NiMH battery packs in models that combined gasoline engines with electric drive, using them to capture energy during braking and supply extra power when accelerating. This was a significant step, quietly weaving battery power into everyday cars and paving the way for the fully electric vehicles that would follow. While nickel cadmium and NiMH were gaining ground for portable and transportation uses, the world of electronics was still yearning for even lighter and more energy-dense batteries. The stage was set for one of the biggest leaps in battery technology since Volta's time, the advent of batteries based on the lightest of all metals, lithium. Lithium is an attractive material for batteries because it is extremely light, the lightest metal in the periodic table, and highly reactive, meaning it can potentially provide a lot of energy. Its ions are small and move quickly, and lithium-based compounds have high voltage potentials. Researchers had toyed with lithium battery chemistry as far back as the early 20th century. In 1912, G.N. Lewis experimented with lithium, but it was not until much later that technology caught up to lithium's promise. In the 1970s, the first small lithium batteries, though not rechargeable, came to market, supplying about 3 volts from a single cell and proving useful for cameras and digital watches with their long life and high energy content. But making a rechargeable lithium battery was far more challenging. Early attempts in the 1970s using lithium metal as the anode showed promise but also serious safety issues, as lithium can react vigorously, even causing fires or explosions if mishandled. Researchers realized that to tame lithium, they needed to find new approaches that avoided using lithium in its pure, highly reactive metal form during cycling. Throughout the 1980s, scientists around the globe sought a safe and practical design for a lithium rechargeable battery. The breakthrough came by using lithium not as a free metal that plated and stripped during charging, but in compounds that could reversibly house lithium ions. In 1980, John B. Goodenough and co-workers identified a lithium cobalt oxide compound that could serve as a high-energy cathode, the positive side. It could host lithium ions and release them at a high voltage. A few years later, other researchers like Rashid Yazami and Akira Yoshino found that certain carbon materials, like graphite or a carbonaceous polymer, could act as the anode, the negative side, absorbing lithium ions safely and releasing them during discharge. By 1985, Yoshino had built a prototype lithium-ion battery using these principles, and it proved to be stable and rechargeable. Importantly, it did not use lithium metal during normal operation. Lithium ions moved back and forth between the carbon anode and the lithium cobalt oxide cathode, embedded within those materials rather than forming pure lithium metal. In 1991, the first commercial lithium-ion batteries hit the market, introduced by Sony. They were initially used in camcorders, bulky video recording devices that demanded a lot of power in a small package, and in the very early mobile phones, which were then the size of bricks. The lithium-ion battery had an almost gentle beginning. The early applications didn't yet hint at how ubiquitous it would become, but those who used them noticed the advantages immediately. Compared to the older nickel-cadmium or lead-acid batteries, lithium-ion cells were much lighter for the same amount of energy and had no memory effect to worry about. They also held their charge well when not in use. Over the subsequent decades, lithium-ion technology quietly improved further. Manufacturers refined the chemistry, introduced new electrode materials like nickel-manganese-cobalt blends or phosphates, and made the batteries safer with better separators and internal protection circuits. Costs gradually came down and energy density went up. By the late 1990s and early 2000s, lithium-ion batteries were powering the new wave of consumer electronics. From the first truly portable laptop computers to digital cameras and the blossoming array of mobile phones that were becoming ever more compact and capable. A laptop from 2005 could run for several hours on a charge thanks to a flat lithium-ion pack tucked underneath the keyboard. People could charge their cell phones overnight and carry them through a busy day, all due to the high energy stored in a slim lithium battery inside the device. Each year brought incremental improvements, a few percent more capacity here, a slight weight reduction there, so gradually that users might not have noticed, except that their new phone lasted a bit longer than the old one, or their new laptop was a bit lighter and ran a bit further on a charge. The importance of lithium-ion technology was finally recognized on the highest stage in 2019, when the Nobel Prize in Chemistry was awarded to 3 scientists, John Goodenough, Stanley Whittingham, and Akira Yoshino, for their pioneering work in its development. By then, lithium-ion batteries had already transformed how we live, though in daily life they remained inconspicuous. They are sealed away inside our devices, doing their work without drawing attention to themselves. In the late 1990s, another refinement appeared, the lithium polymer battery. This is essentially a variant of the lithium-ion chemistry, but instead of using a liquid electrolyte, it uses a polymer gel or solid that allows the battery to be made in very thin and flexible shapes. Without needing a sturdy metal can to hold a liquid, lithium polymer cells could be formed as flat sheets and sealed in lightweight pouches. This suited the era's new devices perfectly. Flat cell phones, MP3 music players, and eventually tablets and ultra-thin laptops. Designers could shape the battery to fit the device rather than the other way around. So, if one were to open up a smartphone circa 2010, one would find most of the interior taken up by a slim, rectangular lithium polymer battery tailor-made to maximize capacity in the available space. High costs and concerns about resource availability have also spurred interest in alternate battery chemistries. In recent years, some researchers turned back to more abundant elements, like sodium, a close chemical cousin of lithium, to see if they could be used for large-scale batteries, for instance to assist the electric grid. By the early 2000s and 20s, prototype sodium-ion batteries were being tested and even introduced in limited markets, like early models of electric vehicles, and stationary storage in 2023. Sodium-ion batteries work on similar principles to lithium-ion, but typically are heavier and store somewhat less energy. Still, sodium is cheap and plentiful, so these batteries might quietly carve out a niche in the future for applications where weight isn't as critical. Meanwhile, a promising frontier in battery technology at the opening of the 2020s was the solid-state battery. Unlike the conventional lithium-ion batteries that use a liquid or gel electrolyte, solid-state batteries use a solid material as the electrolyte. This change brings some enticing advantages: improved safety, no liquid means less risk of leakage or fire, and potentially higher energy density. The cells can be more compact, and some solid electrolytes might allow the use of a lithium metal anode safely, which would boost capacity. companies and researchers poured effort into solid-state battery development. The idea of a car battery that could double the range without increasing weight, or a phone battery that charges in minutes and never risks catching fire, was compelling. By the mid-2020s, prototypes existed, and some small devices, like pacemakers or other specialized electronics, were beginning to use early solid-state cells. The automotive industry in particular was investing heavily, envisioning a new generation of electric cars with solid-state batteries in the not-too-distant future. Now, as we near the end of this long and gentle journey through time, think of how much of our modern life is made possible by the unassuming battery. If you look around a typical room, you might notice a clock on the wall ticking softly, powered by a single AA cell. Perhaps there's a smoke detector with a 9-volt battery standing guard quietly for your safety. A phone rests charging, its internal battery storing energy for your next call or message. Flashlights in drawers, remote controls for the television, the car in the driveway with its battery ready to start the engine, or even drive the wheels directly if it's an electric model. The legacy of Volta, Daniel, Planté, Leclanché, Edison, Jungner, and so many others lives with us each day in these forms. They're all around us, silently performing their duties. The history of the battery is a story of patience and gradual progress, each innovation built gently upon the last, like bricks laid one by one to erect a sturdy wall. From the first static sparks coaxed into a Leyden jar, to the metal piles that gave a steady trickle of current, to the ingenious chemical cells that powered the first communications and machines, and onward to the high-tech batteries of the present day, there were rarely moments of sudden triumph accompanied by great fanfare. Instead, there were many small realizations, many careful experiments, and many incremental improvements, each important in its own quiet way. And perhaps that is why this history carries a soothing quality. It reminds us that great things can grow from steady, persistent effort and curiosity, without haste or noise. As you drift into slumber, consider the humble battery one more time. It is a device that holds within it the power to spark light in the darkness, to carry voices across the night, or to move vehicles without a sound. Yet it does so with no fuss, sealed in a little box working in silence. The journey to create that device spanned continents and centuries through the minds and hands of many dedicated individuals. And now, their collective work resides quietly in your world, ensuring that when you need a bit of energy, be it a light to read by at bedtime or a soothing piece of music to lull you to sleep, it is there, faithfully supplied from a small container of chemicals working in harmonious silence. In the story of batteries, we find not just a chronicle of inventions, but also a reflection of human ingenuity's patient side. It is the side that advances carefully, step by step, storing up knowledge like a battery stores charge, until one day it illuminates the world. So as this tale comes to an end, you might imagine the gentle glow of a nightlight nearby, perhaps powered by a battery, casting a warm, reassuring glow in the darkness. May the quiet energy of this history now carry you into a peaceful sleep, as softly and surely as a battery's current, flowing through a friendly, guiding nightlight.